When we have to design any control law, I will divide the categories under which the gain is changing, specifically when I am kind of fixing the methodology as proportional control only. Then I will look into tuning the gains in different categories. But when I'm moving from one category to another category, is there anything that I should be worried about?
When we try to change the gains abruptly, the actuator may not be able to give that output all of a sudden. So I think that would be a problem in real time. It was in simulation.
So the response time of the actuator, because when you are giving discontinuous inputs, that's what theory says.
Do you think this is scalable? At some level, it would become tantamount to, faced with constant disturbances and undulations or irregularities in your path, this algorithm would be tantamount to like remodeling at every step, and it's going to be very computationally intensive. Because if you're going to readapt these weights, it's exactly like a time varying feedback then, right? It's no longer going to be a constant gain matrix that's going to be fed back. So you're going to be treating the system like a time varying system that way. And I'm not sure that is the way we want to model this. Because, of course, there are distinct changes in the model, in the weights, that is, after post every pick-off or drop-off. But, when you're going along a path and you face disturbances, those are not treated as changes in the model. Ideally, you can consider them as time-varying models, but that's not how we do it. We still model them as LTI systems, and we provide an LTI feedback to design an LTI controller, linear time-invariant controller. Not really a time-varying system as such. But the approach you're adopting, it seems to suggest that, instead of treating these changes as disturbances, you are trying to incorporate them in the model. Now, the price you will end up paying in that sense is a lot of computation, a lot of burden on the computation. Because you are expecting to be able to model this in exactitude. But the goal of controls, on the other hand, is that even with an inexact model, you should be able to design a fair enough controller that should address not just a single model, but a whole family of plant models. You're moving along a straight path. Once you have stabilized something, unless there is some external disturbance, there's no reason for that particular system to move away from its stable equilibrium. It's only when there are disturbances or undesirable forces at play that you are sort of waylaid from that equilibrium, and you want to have a restoring force or power generated which restores you back to that equilibrium, which is essentially the goal of control.
Yes.
Right? So for that, you don't necessarily consider it to be a time-varying system. You consider those to be just that, disturbances. You'll have a huge lookup table for all possible scenarios, all possible changes, all possible fluctuations, all possible disturbances, and you have a lot of if-then clauses. If this, then that. If this, then that. If this, then that. Right? So every time you're constantly sensing and checking and doing that. Per se, I have no problem with that, except for the fact that when you face more complicated scenarios, this is going to be nightmarish, is what I'm going to suggest.
How important it is to be kind of a tinkerer if you want to be an engineer, in the sense that you should be playing with toy cars and breaking things and kind of making them again and stuff like that. And the way I would intuitively relate to this is that if you lower the CG, the ground clearance is less, and you have to put smaller wheels which have other disadvantages. As you raise it, ground clearance is better, and you can put bigger wheels and there might be less rolling resistance and stuff like that. So it just shows that in engineering, it's lots of conflicting constraints that one has to battle with in order to come up with the right kind of design. Professor Shashikant Suryanarayanan in McKen's department, when he was a student at Berkeley, he had a friend who would race bicycles, and they had these very high-powered bicycles where you lie back and you hold the handle in front and you go at speeds of about 90 kilometers per hour and all that. Okay. One of the problems that they had there is that he found it very difficult to maintain a straight path when he's pedaling very hard because your hands move, right? He actually built this guy a steer-by-wire system. It's basically a totally automated steering system where your steering is just giving an input to your control system and the actuation is happening through motors. Professor Dwaipayan also appreciated that when you are in an electronic environment, when you have electronic actuation, you can think of vehicles in a totally different way from human actuated vehicles. Okay. And given the fact that actuators are not that expensive as they used to be anymore, and compute is not so expensive, right? Those are the things that you could actually build a bike with stabilizers of this kind in your steering and all these kind of things.
The one that you have done is easy to get it implemented in hardware because these bikes are anywhere there and you just add on those components and it can actually work in field if you really want to make this useful. That's something that is available easily in the market. You add on some components and then it can do the work rather than completely generating the entire designing and manufacturing the entire system.
When a person is riding a bike and sees some way ahead of himself or herself and discovers that there is a uphill road ahead or a downward slope, the action that you take a priori before you actually encounter the scenario is what is feed-forward action. In an automated bike, I mean, in this virtual environment, you might have put in, I don't know what mechanism you have put in, but you might have put in some mechanism in place to detect when there is a change in terrain and accordingly take action. In a real setting, when you have a bike running without a rider, implementing this feed-forward will entail, I mean, in a realistic setting, like you say, in a village, you have a cow on wheels, right, in a village. So, in a real setting, doing this will entail a lot of sophisticated sensing. You want to take corrective action because that's the price of feed-forward. The reason why people go for feedback as opposed to feed-forward is simply this, that feed-forward requires very sophisticated sensing. So, when you're doing this change of speed according to what lies ahead of you on the road, essentially you are doing something akin to feed-forward, which is a costly thing to do. These days in controls community, we have a lot of emphasis on biologically inspired control strategies. So we try to mimic whatever is going on in the natural world, and we think that animals or ourselves, human beings, we are the smartest people around with brains, right? Not artificial brains. And we tend to think that whatever we do, the way we do things are somehow optimal. I mean, years of evolution has probably taught us that. Right? But then it also comes with some price. Once you are fixated on certain ideas or certain ways of doing things, it's very difficult to train our brains to shift the paradigm and think in different terms. So while I was looking at some of these strategies that have been implemented by students here, it just occurred to me that if we tend to transcend our human barriers and tend to think of strategies that are not just constrained by our commonsensical approach of what is best, right? So sometimes ideas like, this back and forth motion, if we take the human out of the system, there are no such constraints. So it's quite liberating in some sense when you use a lot of autonomy in the system and you're not constrained to move or think as humans move or think, right? So maybe we should try to, instead of always looking for inspiration in the animal kingdom or the natural world, sometimes I also try to think in a counterintuitive fashion and see that things that we don't necessarily do, but robots are capable of doing, might always not be a bad thing. In fact, they might sometimes be more optimal than we might think.
There's a school of thought which goes towards biomimicry, and everybody feels that biomimicry is the answer to all problems and things like that. But the fact is that given this make-believe and engineered world of ours, there are possibilities which are available which might not be found in nature mainly because of how things are. So I think that's a pretty important takeaway from here.